elimination reactions, you thought things were hard when I talked about SN1 and SN2, and then I talked about E1 and E2, then we realized that the chemical life is kind of complex. And in an E1 reaction, you don't have to have a good base, because remember, in an elimination, you're supposed to have a base. It eliminates, so you got to pluck out a proton. Okay, you don't have to have a good base. But you know what? All of those guys here is exactly the same. The only thing I will say is that when you heat it up, heat will favor elimination. It's to do with basically the activation energy, okay, of the two reactions, and it's also really related to the generation. And I didn't want to talk about this, but I just put this down because you already know this. It's really related to this equation over here, an increase in entropy as well. When you eliminate something, you increase the entropy, so therefore it's really related to this equation. But I didn't tell you that, so if you wanted to know, I just told you, but you won't need to explain this, okay? Because it required me to explain another concept which I felt was a little bit too much for your little head, okay? So E1 has exactly the same criteria as SN1. In other words, you come to this carbocation stage, it's not predestined, right? There's no predestination to be SN1 or whatever. When you form the carbocation intermediate, if you get substitution products, it's SN1. If you get elimination product, it's E1. If you get rearranged product, it's rearrangement. Okay? So people ask me, so why does it form an elimination products as well as SN1? It's because the way you think is somewhat different. You're thinking in terms of this is the mechanism, that's the mechanism. But think about the concept. The concept is that nothing is any mechanism, okay? Until you basically have this intermediate, and then you look at the products, and then you say this is a substitution, this is an elimination product. This is SN1, this is SN2. Or E1 or E2. Okay? So this is the sort of thinking that you need to have. In other words, whenever you get a carbocation intermediate, you can have substitution, SN1 reaction, E1 reaction, rearrange product. In other words, if you want to use this synthetically, this is not a very good synthetic route to choose. You will always get mixtures of product. Okay? And then we have this E2, which looks kind of interesting. And for this, you require a really good base. You require a good base because this has analogy to the SN2. You need a good nucleophile. Why do you need a good nucleophile in SN2? Because your lover is coming from the back door, and the current relation, your husband or wife is leading through the front door. You need it to be basically very good for this whole thing to work out, and that's similar to an E2. You need a good base because at the same time, the base has to pluck a proton. It cannot change its mind, okay? Once it's set in some way. It pulls off the proton, it starts off a cascade of reaction which occurs in one step, okay? It's a one-step reaction. The leaving group leaves at the end of the deal. So you have a concerted reaction, which is a one-step reaction. You have an empty periplanar requirement, and tertiary is better than a secondary because of the Zatsier rule, which means that you can form a more substituted product, which means the transition state is more stable when you have a more substituted alkene. Under this, the hardest thing is associated with the cyclohexane system. Why is it difficult? Because it requires you to understand the chain structures of cyclohexane system, which most of you, I know, still don't understand. I know that for sure. Okay? It is not a concept that is easily grasped just by staring at your notes, especially that on the computer. If you really want to understand that, play with your model set. There's no other way I can tell you otherwise. Okay? Right. Let's look at the next set of reactions, which are the addition reactions. They are when you take an sp2 and it goes to an sp3, or, although we didn't do it specifically, you should know, it can be an sp going to an sp2, which then goes to an sp3 carbon. That's the general addition reaction, which is basically on alkenes or alkynes. And they basically means that these guys behave as nucleophiles because they are electron rich. They're going to be able to be attracted to electrophiles that are kind of floating around. And here, I talked about one mechanism, which is an ionic mechanism, where you generate a carbocation intermediate. But you know what? You generate the same carbocation intermediate as you do over here. And so, after when you generate this carbocation intermediate, it can undergo addition now. Now you have the possibility of addition, substitution. Well, the addition product arises from substitution, but okay. Addition, you can get elimination, which gives you back your starting material, or you can get rearrangement. The concept is the same. Here, the important thing to note is the Markov-Nikov rule. Anything that goes through a carbocation intermediate will give you the most stable carbocation intermediate, which then leads you to the Markov-Nikov product. Markov-Nikov product is one where the product is going to arise from the reaction in such a way that you will form the most stable carbocation intermediate. And an example of this is essentially, I'm just going to make up something here like this. Okay, you react it with HBr, okay, and you will have the possibility, because this is going to react with an H plus first, right? You can either form this guy, or you'll be able to form this guy. This is a secondary carbocation, this is a primary, this is more stable. So this is what is going to form, and then we have a substitution step onto here. And then the product that is favored is going to be this guy versus this guy over here. I'm working from first principles, right? This is in the case of an ionic mechanism, which is basically going to be governed by the Markov-Nikov rule. The mechanisms I didn't teach is essentially the radical mechanism, which is the non-Markov-Nikov product. And here, examples are these reagents which I asked you to memorize. I already told you the reactions I needed to memorize. And there are also other mechanisms which are miscellaneous, like hydrogenation with a metal catalyst. All of those ones, where it is noted that you have to memorize, you should memorize. They are synthetically important, okay? And that is why you need to know. There is also another addition reaction which is really weird, okay? That addition reaction is when the alkenes and the alkynes behave as electrophiles. Very special class. They are the Michael acceptors. EWG is not TWGT, okay? This EWG is electron withdrawing group. What does TWG stand for? I don't know. Anyway, okay. So they behave as basically electrophiles, and you can react, for example, this guy at this position. So the end you will get is going to be like that. This is known sometimes, apart from calling it a micro reaction, it's also known as a conjugate addition or a 1,4 addition. Practically, only certain nucleophiles will behave that way, and I didn't want to confuse your mind by telling what they are. Just kind of note that this is the sort of reaction. Not all nucleophiles will react at this position. Some will react at the carbonyl. One page, okay. Essentially substitution, elimination, addition reactions, and we are now nearing the end because we are going to think about the last few things that we did, which is carbonyl chemistry. And in general, carbonyl chemistry can be divided into aldehydes and ketones. And carboxylic acid derivatives. And the things that we need to remember in general is that when you look at these categories, you know actually from what I described to you, although I didn't tell you that at the beginning, is that these guys, okay, can behave both as electrophiles and nucleophiles in general. They are schizophrenic, I said. Okay? And under the fact that it is electrophilic, it will be able to react theoretically under addition reactions or addition elimination reactions, which is basically only specific for nitrogen nucleophiles. In the case of it behaving as a nucleophile, this leads to the concept of tautomerism because you have an acidic hydrogen and the tautomers are enol, they are enol under acid conditions and they are enolate under base conditions. And so these guys behave as nucleophiles. Either they are enol or enolate, they behave as nucleophiles. Which means that when you combine these together, when it behaves as an electrophile and nucleophiles behave condensation reactions, which is aldol reactions and variations thereof. And then if we look at carboxylic acid derivatives, we need to know who are the members of this clan, okay? And then you need to know what is the reactivity order, who is going to be more reactive, okay? And you need to know how to synthesize certain derivatives. Okay, for example, how do you convert an acid to an ester? How do you go from an ester to an acid? Okay, and so on and so forth. Remember the pyramid, okay, where this is the acid chloride, okay, the bottom of this was the amide, this is a reactivity order, and you need to know that actually why this is more reactive than that, okay, and how you're going to be able to make something like this from something like that. Very easy. We discussed that briefly as well. finally, we have aromatic chemistry. And you know what? There's only one type of chemistry that I tell you, which is the electrophilic aromatic substitution reaction, EAS. And so, when we looked at this, I started off being very, telling you essentially in a very simple system, which is this guy. You need to know the different electrophiles to give you the different products. I asked you to look at this, and you need to memorize this. Remember the one that we talked about the different electrophiles? You need to know the conditions and the mechanisms. For example, if you want to make nitrobenzene from benzene, you will use nitric acid and sulfuric acid. If you want to make bromobenzene from benzene, I'll use bromine and FeBr3 or AlBr3. You need a Lewis acid catalyst because the benzene is not really that reactive compared to an alkene because it's electron rich and it's a clump. It basically has this special stabilization. So you want to entice something to break out of the norm or a position of stability, you need to make sure your electrophile is very good, which is why you need a Lewis acid. Okay? And then we look at substituted derivatives like this. Okay, and here you need to work out how fast is it going to react? Is it faster than benzene? And how selective it is? In other words, is it autopara or meta-reactive? In some sense, you are able to tell me, okay, that if you can explain all of this, this is going to be pretty good. Okay? And some of the substituents you will see, you will probably not seen before, maybe, but you should be able to work it out with first principles. And some wise guy is going to tell me what happens when you have substituents, more than one directing group A, and they are counter each other. The example I showed you earlier on with the benzodiazepine. And sometimes if the donating power, okay, of those are the same and they could give you different radioisomers, basically you should know that you might get a mixture of products. In other words, I'm saying in situations where A and B, okay, you've got more than one substituent, where is it going to be able to react? This is something that you should be able to work out, and practically I will give you questions where it is going to be quite obvious the answer. Okay? Either I give you an answer, the product, and ask you to explain it, or if I ask you to predict the product, then you need to be able to rationalize this, okay, in terms of the different strength, but it should be obvious. And that is really all, okay, that is really all that I have to teach you in this portion of the work. And I realize it's now 9:10, which is neither here nor there. It's not going to be enough time for me to do a 2 question, okay, which I guess we can do in a little while. Maybe I'll just flash a question up, okay, but before that, I would like to know if there are any queries associated with the summary.